Well, thank you guys for coming out today, for sticking it out until the end of the session. So, as he mentioned, my name is Ryan Schonert, and I'll be talking today about the analysis of non-traditional gasoline additives using GC-VUV. Now, if you were here to listen to the talks by Alex and Jack, you would know that they're a lot more experienced than I am. Gasoline analysis is a pretty new endeavor for me. But I do remember the first thing I ever learned about gasoline when I was a high school teenager. That would be this. That gasoline can be a bit expensive if you're a high school teenager. Of course, as I would come to learn, especially after starting at VUV, is that there's a lot of stuff going on in gasoline that you might not be expecting. And one of the major parts of that is that there are a lot of gasoline additives put in. And so when I'm talking about gasoline additives, I'm simply talking about organic compounds that we put in our fuel to adjust its properties. And these are inherently added during the refining process, but you can also buy them at the store if you want to supplement your gasoline even more. Some of the more major components we see are maybe better referred to as major fuel blending components. And these are very important for certain properties like boosting the octane rating or preventing pollution. And a lot of these are blended at the volume percent level, so in larger amounts. And in the context of this presentation, these are the types of compounds I want to talk about. So before I go into some non-traditional additives, I just want to talk over maybe a few additives that you might know more about that are more commonly seen. One example is methanol here. Methanol is a compound that we use because it does a good job at boosting the octane rating. It's cheap. We can get it from a lot of different sources. It burns very efficiently, and all that is good. But what we see is that when we look at the emissions, we're spitting out a lot of formaldehyde into the air, which of course is not good. Another one is benzene. For many of the same reasons that methanol is used, benzene is used. It boosts the octane rating. It's part of a larger group of compounds called BTEX, or benzene, toluene, ethylbenzene, and xylenes. So it's very important, but as you may know, very toxic. In fact, it's been labeled by the International Agency for Research on Cancer as a Group 1 carcinogen. And for that reason, even though it's very useful, we have to limit it down to very small amounts in our gas because of the potential health risks. A third example is one that's maybe not used so much here in the U.S. anymore. We do see it from samples outside of the country, but that would be MTBE, or methyl tert butyl ether. The reason this was used historically is because when you're wanting to increase the oxygenate content of your gas, there's a fly flying around my head here. This is something we could use to boost the oxygenate content of our gas. It's very easily blendable into our gasoline, which is a good thing, but various research ended up showing that MTBE is water soluble and very environmentally mobile, meaning that it could make its way to drinking water sources like groundwater. And all the potential health risks aside, you might even see a noticeable difference in taste and smell, none of which is good. And so you can see that a lot of additives like these have pros, but they also have cons. And so this has kind of led for a search for new gasoline additives. And so when we're talking about non-traditional gasoline additives, one perspective of that is that we're looking for new additives to give us the same effects that we need, but are also, as a bonus, perhaps environmentally safe and renewable. And so I got an example here on the screen. With this chart here, this is talking about ethyl acetate, and the chart shows that when you add ethyl acetate in successively higher concentrations, what we observe is that the octane rating is going up. And that's a good thing. Some other benefits that ethyl acetate has is that when you look at the emissions, the carbon monoxide concentration goes down. And in addition, it increases the stability of your gasoline as well in terms of water tolerance. And so, of course, when you're, say, producing and transporting gasoline, water coming even from the air might dissolve in your gas. But once you get a certain amount of water in your gasoline, you'll see a phase separation, which is not good for your engine. You want to prevent that. And so adding ethyl acetate can increase your gasoline stability by allowing more of the water to stay dissolved without separating into two phases. Some other compounds that I thought were interesting were these furan compounds here. The reason I thought that these were interesting was more about how they were obtained. So this research group here, they wanted to see if they could get usable gasoline compounds from biomass like pineapple residue. And so what they did was they went and took some of the pineapple residue, like the crowns and the stubble, and through a little chemistry magic, they were able to get these compounds out, which I think is a very creative way to supplement your gasoline. And in fact, what we see is that there is a lot of potential for gasoline compounds derived from biomass in that same way. This is just a partial list outlined by one research group, but we can see even in their list that we've got all sorts of different compounds. So we've got alcohols, alkanes, alkenes, esters, ethers, furans, ketones, and of course there are more out there yet to be discovered. And so I would call those maybe good additives, ones that we're trying to develop. But on the other side of the coin, we have some problems that we have to address as well when it comes to new additives. For example, in 2014, the Asian Clean Fuels Association released this list of 5 compounds that they were starting to see in gasoline that were being problematic. They're added because they can increase the octane rating, which is, again, a good thing, but they also have some cons as well, namely that they cause engine problems, human health problems, and environmental problems. And of course, these are things we want to avoid, especially as environmental conditions are becoming more of an important issue. And so just as an example, we can look at N-methyl-aniline here. As I mentioned, this is added as an octane booster, but it's got some issues. Number one, it forms gum in your engine. So gunking up the inside of your engine will decrease the effectiveness and health of your engine, and it can also swell rubber seals. So when the N-methyl-aniline reacts with your rubber, it swells and may cause things like oil leaks to happen. And so we've got to keep an eye out for these things too, because many of these are outlawed, but we need to keep an eye out just in case they're trying to sneak past the regulations here. And so when we talk about gasoline analysis, and this is something that a lot of you have probably heard a number of times today and yesterday, is that DHA, or detailed hydrocarbon analysis, is kind of the gold standard for analyzing your gas. That's per the ASTM method of D6730. And this is a method that's been proven. It works very well, but it does have some drawbacks that I want to address. First of all, we're looking at a very long runtime on the order of 2 to 3 hours for a single sample. Another one is that, at least in the context of a GC-FID run, you're only going to be able to identify your compounds generally by retention time. You can include some mass spec work in that as well, but that only adds to the complexity of the run and the length. So that's not necessarily always a good option. And finally, and maybe most importantly for the context of this presentation, it's that we can't really add new compounds to the scope of this method very well. Changing an ASTM method is a lengthy process, and maybe not the best process we want to go through given the length of time we're already dedicating to each run. And so what we're proposing is that maybe this isn't the best way to go going forward. And so now I want to take a step aside here and talk about something else, what we're proposing, and that would be VUV, or vacuum ultraviolet spectroscopy. And so you've probably seen this diagram a number of times if you've been to any of the other VUV talks, but since it's a relatively new technique, I do want to address some of the major points with it. So as you can see, we've got our GC oven here, and as our compounds are eluting, they go to a flow cell where they interact with the stream of ultraviolet light provided by a deuterium lamp. And so as the compounds interact with this light, they absorb some of the UV light, leading to an absorption profile here. And this absorption profile is unique to each compound coming through. And we'll show some examples later. But they're especially unique when we consider that they're in this range here, from 125 to 240 nanometers, because essentially all compounds will absorb in this range. Another maybe misconception you might have about the technique based on its name is that there are vacuums involved. But as it turns out, no vacuums are needed. This is because historically, to get this type of data, as Alex mentioned with synchrotron laboratories, you would have to have an evacuated chamber to get this type of measurement, which is not an easy thing to do. If you've worked with mass spec before, you know that vacuums can be very finicky things. They don't like to be troubled. So not having vacuums involved in the process is actually a good thing because it gives us a very rugged instrument, but it also gives us some chromatographic options as well. For example, with a mass spec, your flow rate is very limited because you don't want to overwhelm your vacuum. But with a VUV detector, with no vacuum, what we find is that we can pump up the flow rate to our needs because, once again, we can do this at ambient pressure rather than at a vacuum. So that just gives us some more options to work with. And so here I've just got some more examples of the type of spectra you might be able to get with a VUV detector. And so each of these are 6 carbon hydrocarbons here of different types. So we've got a paraffin, an olefin, an aromatic, and a ketone down here. And what you can see is that in each of these spectra, we have a lot of features, both major features and even subtle features, that we can use to differentiate our compounds. And some compounds that we look at have really rich and unique spectra. I include this one here for 2,5-dimethylfuran, both because I think it's a cool looking spectrum, but also because this is actually one of the compounds we looked at in this experiment. So using these types of features, we can do a good job of differentiating these compounds. And probably one of the most important aspects of using VUV for this type of work is that we can handle coelutions very well. And so when we add a new compound, say, such as acetone to our gasoline, and we want to see, well, can the VUV detector pull it apart from anything it coelutes with, we find that we can do that. And so this is some data I took from, or this is a graph I took from some data that we collected here. And in this case, we see a coelution of acetone and isopentane. And you can see that even though they're coeluting essentially on top of each other, I still know which compound goes where and what's contributing to this overall peak that we observe here. And the reason we can do that is through the spectral library matching with VUV. And so here you can see the overall spectrum that we collected and what we observe, but through the spectral matching, what we find is that we can tell what compounds are summing up to form the spectrum. So I like this graph too because if you take a close look at it, you can really see how each of the individual spectrum sum up to give us what we observe. And there are some unique features in each spectrum that you can see very well. For example, out here from 180 to 200 nanometers, we can see that acetone is the sole contributor to these peaks out here. And these are the sorts of features that we take advantage of to separate our compounds. And so the standard method that uses GC-VUV is ASTM D8071. Now this type of analysis is a Peona analysis, so gathering data for paraffins, isoparaffins, olefins, naphthenes, and aromatics, as well as a select few other compounds. And just some highlights of this method here is that we have a runtime that is under 35 minutes, so about 33.5 minutes, which relatively speaking is much, much shorter than a 2 to 3 hour DHA run. We also get a lot more confidence in our identifications, so we're identifying compounds not only by their retention times, but also by their absorption profiles. We do have the ability to deconvolve coeluting compounds, as I just showed you, which is very important because if we're adding new compounds into our gasoline, we don't want to have to mess with our method if we don't have to. And so this spectral deconvolution becomes very important. And finally, because of these reasons, we're able to add compounds to the method's scope a lot more easily. And so our experimental question was, well, can we take these method conditions and use them to analyze our gasoline samples for the presence of these additives? So on to the experiment itself. I've just got a quick picture here of our instrumental setup. We're using a VGA 101 with an Agilent GC. So our experiment itself was divided into essentially 3 steps here. Number 1, we made some volumetric standards of different compounds in oxygenate-free gasoline, or oxy-free gas. And I've got the list up here. I believe there are 30 of them. And we made them at these concentrations, so at 1, 3, 5, and 10 volume percent. And for a select few, we actually took it a bit further and went all the way up to 20% down to 0.05%, just to see if we can handle this extended concentration range as well as the normal range we're looking at. And so once we had our standards prepared, we took them to our GC-VUV, and we used the ASTM D8071 method conditions to run them. And I've just got a quick snapshot of the method here. No need to read this bullet by bullet, but just a few highlights here. Number 1, you can see that our column here is a 100% PDMS column, which is, I think, a pretty standard column for most analytical labs to have. And you'll also notice that there's no pre-column necessary. So that kind of takes away from the complexity, makes it a little easier to run. Another thing is that, again, with these oven parameters here, we've got a run time of about 33.5 minutes, which, again, much shorter than a DHA run. And finally, we're collecting out in the 125 to 240 nanometer range, where there are a lot of unique spectral features that we can take advantage of. And finally, once we had all of our data collected, we went and calculated the concentrations of each of our additives. And because this is a spectroscopic technique, we can simply use the concepts of the Beer-Lambert law to quantify everything, because absorption is proportional to our concentration. And so here I've got the data, and once again, I don't expect you to sit here and read every line, but if you take a general look at some of the numbers, what I hope that you see is that for a first pass at this type of analysis, we're doing pretty well. We're getting very close to what we expect here. Those of you with a very keen eye might notice that one of the numbers looks a bit strange. That would be this one here. When we go out to 10% by volume for gamma-valerolactone, we notice that we're getting a much lower response than what we expected. And well, why is that? We did some investigating. It didn't take too long, actually, because once we started to make some more samples, we found this out very quickly, is that when we tried to make these samples, what we were noticing was that we had a phase separation here. And so past a certain point, the gamma-valerolactone becomes insoluble, and we see a phase separation. Well, why is that? Like I said before, we used oxygenate-free gasoline for these standards, and that means no ethanol, which, as it turns out, is a very important factor here, because gamma-valerolactone is a very polar compound, and it really needs that ethanol to dissolve. And so we simply just decided to remake the standard, except we used a regular E10 gasoline, Murphy Express gasoline in this case. And when we made this solution, we found that it was soluble. So when we looked at the numbers, this is kind of what we were expecting. Everything dissolved, and so when we look at our results here, we're once again very close like the rest of our data. And so as you can see, even with that minor issue here, we're getting very close to the data that we are expecting. And these are the results for the samples we did at an extended concentration range, so from 20% down to 0.05%. And once again, when you take a look at these numbers, we're doing very well, getting the results that we expected, especially when you go to the lower concentration ranges down here. You can see that we're pretty close. And so the results are indicating that we're doing a pretty good job so far, especially for, like I said, a first pass at this type of work. And so for those of you visual people out there, I just want to graphically go through some results here. So here I've got the results for dimethoxymethane. And if I didn't mention this before, we actually ran each of those samples in triplicate. And what you may be able to see is that there are 3 samples plotted here at each concentration, but they're grouped very well together, so we're getting very consistent results down to 0.05%. And what I also hope you can see is that we're looking at very linear results here, judging by the peak sizes and shapes. But if I were to make a calibration curve out of this, what you might notice is that we do a very good job at getting linear data. So if we plot response versus concentration, what we see is that our R squared is very good, up well over 0.99, meaning that we're getting a very good linear response and that we're quantifying very well. Another plot that we did is pretty similar, just a linearity plot, where we plot the measured volume percent or concentration compared to the expected volume percent of what we spiked in. And if you take a look at our slope, you'll see that it's slightly over 1, meaning that our samples are a bit biased to be a little higher than what we expect. But looking at this R squared, once again, we're getting very linear data, and that our samples are being quantified very consistently, which is good. And so I already showed you guys the graph of acetone and isopentane co-eluting, but just because, once again, this is a very important aspect of the method, I want to show it off one more time. So if we take a look at ethyl acetate, I've got the 10% ethyl acetate peak highlighted here, and we can zoom in on that peak, and this is what we see. So in black, we've got our overall peak that we observe, but we can see that there are 3 compounds contributing to that peak. Mostly ethyl acetate here because it's at such a high concentration. But if we were still interested in, say, our hexane here, or even this trans-2-hexene, we find that they're getting lost in the giant peak here, which could be not good if you're still wanting to look at your Piona-type data. But once again, because of the spectral library matching, we're able to go in and see that even though we have our combined absorption spectrum here, we're still able to see that there are different compounds contributing to the spectrum. And for example, here, this feature between 160 to 180 nanometers is mostly from ethyl acetate. And so features like that are the reason that we're able to tell these compounds apart very well. And so just in conclusion here, when we're looking at our non-traditional gasoline additives, we find that we can successfully analyze these compounds with GC-VUV using the ASTM D8071 method conditions. I've got, again, the major points here of why we can do that, because we can add new compounds to the library very easily. So if we come across new additives of interest, or if we start seeing other additives that we want to make sure we keep out of our gas, we can see them just fine. And again, if we're looking for these types of compounds, they're not going to be hidden away in our other peaks because we can deconvolve them and we can quantify them very well. And because of those reasons, we propose that this is a better route than continuing to rely on DHA because we've got a much shorter runtime. When we identify our compounds, we have a lot more confidence, both from the retention time and the spectral matching. And again, no need to change the method conditions. All we simply need to do is run a standard to get a reference spectrum. And once we nail down the response factor, we'll be able to quantify them very well without needing to change the GC run. And with that, that is all I have. Before I just want to mention real quick that if you guys want any of the presentations, this one or maybe Jack's, James, or Alex's presentation, feel free to contact one of us. I've got my email up here and we'll be around after the presentation. So if you'd like these slides, feel free to come talk to one of us or email us. And with that, that is all I have.